10-2, graphing, cube root functions. What? 2 sections in a row and 2 new functions? This is out of control. We've studied absolute value functions, linear functions, exponential functions, quadratic functions. 10-1, we did square root functions, and today we're doing cube root functions. Hopefully you see what's happening here. If you understand the basics of how things work, you can learn all sorts of functions very quickly because you already understand things like transformations and how those transformations look, etc. So, essential question, how do I determine which inputs to use when graphing a cube root function? Because when you're graphing it, you're going to have to determine what your inputs, your x's are, and there's a little bit of a science to that to make it easy for us. So, cube root functions, here they are. A cube root function is a radical function with an index of 3. That index of 3 thing, which sounds really crazy, it's just the number outside the radical here, which tells you what root you're taking. If there's no number there, it's a square root, so the index would be 2. The parent function, of course, the most simple version for the family of cube root functions is f of x is equal to the cube root of x. No transformations, as simple as possible. The domain and range of f are all real numbers. Oh, yay! That's different than the square root function. Remember, the domain of the square root function was restricted by the fact that you can't take the square root of a negative number. So in the cube root function, though, we don't have that problem because you can take cube roots of negative numbers, which is really sweet. The graph of f of x equals the cube root of x, that's the family, or sorry, the family, that's the parent function. Oh, it's the parent of the family, increases on the entire domain. What does that mean? As you read left to right on the domain, that means on the x values, this is increasing, it's increasing a little more steeply, still increasing not as steeply, but it's increasing all the way. And you can transform the graphs of cube root functions, I suppose I should be highlighting, transform graphs of cube root functions in the same way you transformed graphs of square root functions. So this is that, you know, you put in the work before, all that a and h and k business and how those transform the function. You've put in that work. This is easy. You've already done this before. Okay, so let's observe this graph a little longer, make sure we understand what it looks like. If you're really paying attention, and you probably are, if you only see the highlighted part, ignore this bottom left part, this looks like a square root function graph right here. This looks like a square root function graph. But whereas, remember, there was kind of the origin of the square root function graph, this one keeps going. Why? Because you can take cube roots of negative numbers. And so it's just basically this same graph reflected going in the opposite direction, I guess double reflection, as you move to the left. It's described as a cube root function graph, or like an S shape, maybe, I don't know, however you want to describe it, but I'm going to probably just use cube root function graph. Okay, graph h of x equals the cube root of x minus 4, and compare the graph to the graph of that's the parent function, isn't it? All right, here we go. Let's think about this essential question. So they've already chosen 2 of the inputs here. They've chosen -8 and -1. Why? -8 is a perfect cube. Its cube root is -2. -2 minus 4 is -6. -1 is a perfect cube. Why? Because the cube root of -1 is -1. -1 minus 4 is -5. What's the next perfect cube up from -1? It's 0. So what we kind of have to keep in mind here is that these perfect cubes are going to be really helpful when finding inputs for our table when we have to graph. And so let's just make sure we understand the perfect cubes. And we can come at this from both the negative direction, so there's kind of an ellipsis, right? It comes in from the left. We have perfect cubes like -27, right? 3 times 3, -3 times -3 times -3. And then the next one would be -8. And then there'd be 0. Whoa, I forgot -1. Hold on. -1, 0, 1, 8, and 27. And then it goes on for infinitely in the other direction too. we need to keep these perfect cubes in mind as we graph these things. As we graph them, we want to make sure we keep them in mind. So our next input after 0 would be 1, and then the next one would be 8. Okay, substituting 0 in for x, the cube root of 0 is 0, minus 4 is negative 4. Substituting in 1, the cube root of 1 is 1, and that's minus 4 is negative 3. And substituting in 8, the cube root of 8 is 2. 2 minus 4 is negative 2. And you'll get a pattern emerging, right? If you choose perfect cubes or numbers that will result in a perfect cube in the radicand, then you're going to get these patterns going on in the outputs. And as you can probably see, function h is the same as the parent function f, except for it subtracts 4 from all the y values. And so here's the parent function's graph. And then if you just translate 4 units down from every point on the parent function, you get to function h's graph. All right, that ends it for part 1. And I will see you back in a jiffy for part 2.